All right, so let's look at mathematical relationships in physics. Okay. So a lot of this is based on stuff you've already taken in math class, and we'll just refresh you on that a little bit. Okay, and we'll start with a little Cartesian plane here, and we will define these as x and y axis, okay, and this is the origin or 0 point, okay. Now this is kind of the math way of looking at this. In physics, these will actually be meaningful things. So for instance, as an example, let's imagine that this axis, the x-axis, represents time. Okay, let's say it represents time, and that the y-axis represents distance. We'll call it d. Okay, and let's say just over here, make it a color we can see. You have a number line, and on this number line, you have an object that is moving along. Okay, so let's say this is 1, 2, 3, 4, 5 meters, and the object starts at the origin, and it kind of moves along to the right at a steady rate. Okay, so it's moving along at a steady rate to the right. So this might be time equals 0, and this might be time equals 5 seconds. So if we look, basically this is covering 1 meter every second. And if we then transfer the time over to this axis, so we said 5 seconds, so there's 0, 1, 2, 3, 4, and 5 seconds. Okay, and this is meters over here. 1, 2, 3, 4, 5. Ooh, my spacing's not quite right, but deal with it. Okay, this is in meters. What you'll end up with is a graph that looks something like this once you fill in your space and your time, right? So what we've done here is we've looked, well, at 0, 0, we're at 0, 0. At 1, 1, we're at 1, 1. At 2, 2, we're at 2, 2. 3, 3, 4, 4, and 5, 5, right? We're reading our graph and transferring it over to here, okay? And what you might have, just to lay everything out here, is you might have something like this, where this is your x value, and this is your y value, in this case time, and in this case distance. And you might have 0, 0, 1, 1, 2, 2, and so on. And usually you would have the units here as well. So that's seconds, and that's meters. Okay? And this would continue on for as long as you've been taking data. All right? So we're representing something in the real world. Okay? We're putting it into a table, and then we're transferring it to a graph. And this could be done by hand on chart paper, or you could use something like a graphing calculator to input this information and see what kind of relationship you're going to get. Okay, so that's example A. Now, let's just talk quickly about the concept of variables, because variables come up here. Okay, so there's two types of variables. There's independent, okay, and there is dependent. And these are often, as a rule, shown as independent variables on the x-axis. So in this case, this particular case, that's time. Time is the independent variable. And the dependent variable, what depends on the independent variable, right? So it's dependent on this. In this case, it's position, really. It's not really distance, it's position. What is the position of the object? Okay? So independent variable, usually this is defined as what you control or measure against. Okay? And this is what changes due to what you are controlling. And when I say controlling here, I'm saying it in a way that means you're sort of changing things. I'll show you an example of that in a minute, okay? What changes due to what you are controlling or what you are measuring against. Or sorry, let me say that right. We're measuring, okay? So in this case, what are we measuring? Well, we're measuring the position, and what are we measuring against? We're measuring that against time. So in a way you could argue we are controlling time, and we're seeing what happens against time. As time changes, what happens in my position, okay? Now, this is called a direct relationship, okay? So if I look, my distance changes directly with relation to my time, okay? We get a linear or direct relationship here. There's no curves, there's no wonky things here. As long as everything stays the same, this will continue to go on forever and ever with this relationship, okay? We're going to go back and show a nonlinear one in just a second. So in a linear relationship or a direct relationship, like the one we've shown, we could say that y will always be proportional to x. Or we could say that position, since that's what we're talking about, position will always be proportional to time, as long as velocity stays constant, right? So sometimes there's some caveats in here, but in this case, that's clearly what's happening, okay? So you will get, on a graph, a straight line if your relationship is direct, okay? So this means then that the independent variable changes directly with changes in the x. As time goes on, as time gets bigger, position gets bigger, okay? Direct, simple, straightforward. Let's go to a less straightforward example, okay? So we'll go to something you've dealt with before, and that is an accelerating object. Now let's say instead of something just traveling along at a constant rate of 1 meter per second, okay? And we'll talk about slope in just a second, okay? Something traveling along at 1 meter per second, let's say we drop it, and we say we're dropping it from height 0, and it's dropping this many meters. Well, what you'll find is, after the first second, it'll actually be going 9 meters per second, and we'll have covered half that distance. So what you get then, maybe we won't say dropping because it would be off our chart, but let's just imagine that this object is speeding up, like it's a car at a stoplight and it's hammering on the gas. Well, it might cover 1 meter in the first second, it might cover 2 meters, so now it's at 3 in the second, and it might cover 3 meters in the following second, and then so on. So in other words, the distance that it's covering per second gets higher and higher and higher and higher. So what will we get on here? Well, let's mark it down. At time 0, we're at the same position. At time 1, we're still at the same position. But by time 2, we're now at 3. At time 4, we're now at, I don't know, somewhere up here. What will we be at? So we went 2, 3, so 6. Is that right? Yeah, because we covered 1, and then we're going to cover 2. Now we're going to cover 3. 1, 2, 3. So we're up here at 6. So now we have something that looks like a curve. Okay, I made that a little too steep, but I think you get the meaning. So if something is speeding up, it's covering a larger amount of distance every second. Okay, this is no longer considered a direct relationship. Okay, and it turns out that this is governed by a squared relationship. So in other words, the distance is proportional to the square of time, right? So if you increase the amount of time by 2, you're going to end up going 4 times farther than if you were doing a linear relationship, okay? So this can be called, it's hard for me to name it, I don't know, I guess exponential is probably the best word for that. And this is where y is now proportional to some raised power, okay, and we'll call it n of x. In the case above, it's square, but it could be cubed, it could be to the power of 4, and so on. And these relationships do exist in physics. Squared relationships are very common, but there's some power relationships that go extremely high. There's a black body radiation formula with a 4 up here, right? A 4 to the power of 4. If we talk about the volume of a sphere, say, right? Imagine the volume of a sphere. If we increase the radius, the volume increases at a cube, right? So that's a cubed relationship. So in these kind of relationships, you get curves, right? And with a direct relationship, by the way, you can also have, it can be direct, but it can be negative, right? So it doesn't have to necessarily be positive. It could be a negative relationship. Like if we were traveling to the left, okay, you would have something that looks like this. Yeah, exponential like that. And I mean, you can have variations on this as well. Negative exponential and so on. You could have stuff like this. Oh, I should be careful. No, forget that one. Nope, my bad. Not right. It's different. Okay, just stuff like this. So that's exponential. And there's a few more you might run into. There's a square root relationship. Or it doesn't even have to be square. It could just be any root. It could be cube, quad, whatever. Okay, and that is where y is proportional to the root of x. That's going to look kind of like this. And what else can I think of? Oh, inverse. What does an inverse relationship look like? Anyone know? Okay. So it would be more like this, right? An inverse relationship where we have y is proportional to the inverse of x. As x gets larger, y gets smaller, right? Does that make sense? As x gets bigger, y gets smaller. As x gets smaller, y gets bigger. It's asymptotal. It'll never intercept these lines, right? It can't, mathematically. And inverse is interesting because you can have different kinds of inverse. You could have a raised power inverse as well. And an inverse square is a very common relationship in physics. So if you put a square here, the graph's going to look more or less the same, all right? But the increase in values as you go here, or the decrease as you want to call it, will not be, say, linear as it is here. It'll be to the square of. Okay, so this is an inverse square. Inverse square laws are very common. There are potentially a couple of other kinds that you might find, but these are like the big four. Okay, the big four types of relationships you might find by measuring stuff in nature and putting it on a graph. Okay, now let's do an example of something we may have seen before. And this is the speed of sound versus temperature. So if you actually went out and measured the speed of sound versus temperature, you would find that the colder it gets, the slower sound travels. And we had a little formula given to us that told us how that worked. It was this. V is equal to 331 plus 0.6 t. Okay? I'm just going to rearrange this. V equals 0.6 t plus 331. Does this format look familiar to people? Now remember, in this case, this is the dependent variable, right? What the velocity of sound is dependent. This, say, is the independent variable. This is what we are measuring against. So I might go outside on a minus 20 day and measure, and I might wait for it to warm up. Okay. In a sense, I am controlling temperature myself. I'm measuring when the temperature is something that's interesting to me. Or I have some kind of facility where I can change the temperature with a thermostat and I'm measuring sound there. Okay. So I am controlling the independent variable. It sounds weird. Well, it's independent. It's independent of the dependent variable. It's what I am changing, and the dependent variable depends on what I do to the independent variable. I think you cover this in math class, actually. So before we said that the dependent variable was graphed on which axis? Dependent variables go on which axis? The y-axis, right? There it is. Written out for you. It's on the y-axis. So could we then say v in this case is like, it's the y, okay? And then t, the independent, is like the x. Y equals 0.6x plus 331. What does this format mimic in your mind? Perfect. Your standard linear relationship that you learn in math class. Well, here it is in a real life formula that you can go and look up in a book. So if we were to graph this, what will we see? Well, we would see we have a Cartesian plane here. We would see this. We would have our velocity of sound here, and we would have our temp here, and we would have to push this back into the negative plane here. The reason being is that we can use negative values on this, right? And we would find that if we looked here, what velocity must be here? This is our y-intercept, right? So what is in our y equals mx plus b? What is our y-intercept? 331. That's 331 meters per second, and then it goes up. Okay, and we also know something else. Okay, B is temp. We know that this must happen at 0 degrees Celsius. Why? Because when temperature is 0, V is equal to 331, right? 0.6 times 0 just leaves us with 331. That's y, that is our y-intercept, or B, okay? So we know at 0, this is going to be here. And we know that for every degree increase, we go up by 0.6. So 0.6 in this case is equal to what value? The what of this graph? The slope. The slope of this graph, which is m, is 0.6. That means for every degree we move over, we move up 0.6 on the velocity scale. Does that make sense? So what we should end up with is a relationship that looks like this. Where's a nice color? Here. Okay. Okay. So this is something that you've learned in math class that we are now translating over to physics. Oops. And really, this is kind of the point of learning all that stuff to begin with. So you can do something useful with it. Y equals mx plus b is interesting on its own, sure, and you can extend a lot of your math knowledge with it. But what's it for? What it's for is for describing the world. And this is one way where your mathematics comes into the real world, right? So if we wanted to find the slope here, what we would do, if say we had a data table to begin with, instead of building this from a formula, we were looking to find the relationship, right? We might have our velocities, and we might have our temps, right? Or our y's and our x's, and we would actually fill this in from measurement, and we would mark points along our graph, and we would draw this out, okay? And then we would come in here, and we would measure a run versus a rise and run, and that should pump out the value of 0.6, right? If we actually calculate this, this rises at a rate of 0.6. Every degree Celsius increases velocity by 0.6. Does that make sense? Okay, that's nice because it's already linear. It's already linear. But what happens if we get data that's like one of these other ones that we saw? What if we get a weird curve? How can we find out what the y equals mx plus b relationship is in that case? And that's kind of where we're headed with this, okay? We're going to learn how to use some techniques and some tricks. I won't call them tricks. I mean, it's just math at the end of the day, to deal with a scenario where it's not in a nice y equals mx plus b format for you, where let's say you take a bunch of measurements and you get strange data. Well, what are you going to do with it? Because really, if we have a dependent and an independent variable, okay, regardless of what relationship we end up finding, whether it be something like that, something like this, you know, maybe even just something simple like that, whatever it happens to be, we should still be able to find an equivalency or an equality between the two. Y equals mx squared plus b maybe. Or y equals m1 over x plus b. Maybe it's that. Or maybe it's y equals m1 over x squared plus b, etc. So how do we get there? That's for next class.